So let us start the lesson today. If you remember, we talked about r-Permutations last time, and there were three problems which were, I think, interesting to solve, and I let you to think about it. I hope that you took this screenshot and you were able to think about them. If not, because that's an important part, I want to make sure that we know how to solve that problem. So I repeat those problems again today. So these two examples are similar together, but there are some differences as well. So how many permutations of the numbers 1, 2 up to 9 are there such that no two of the numbers 1, 2 and 3 are adjacent? So you don't want to consider a scenario like this. I don't know, 6, 7 continues, because you see that, and of course 3 is here. This is not acceptable for this problem, because even though 3 is not adjacent to 1 and 2, but I am supposed to consider those cases that no two of these two numbers is adjacent, so this is not desirable. Okay, but for example, on the other hand, if I have 2 here, 5 and 7 here, 3 here, I don't know, 9 and 6 here, and then 1 here, that is acceptable, of course, until I have to complete all of it. I need to use 9 of them. But you see, this is good because 1, 3 and 2 are appearing here, and they are, none of them are adjacent actually. So I want to start counting all these possibilities. Okay, but because you know that combinatorics is like this, if you don't think yourself, there is no point. I can explain that to you, you understand that. But in principle, if you want to solve harder problems, you need to come up with the ideas yourself. Okay, and of course it doesn't necessarily mean that the idea that I have in mind is the best one. Might be you can come up with a better solution. Okay, so I want to give you a little bit of time. I don't know how many of you have already thought about this problem. If you have already done and have the solution, just keep it for the time being. Let others also think about that, and then we can come to a discussion about these two problems. Okay, so I think I can give you at least 5 minutes. You can at least to think about the first example. Okay, so I stop the video here, so you can start thinking about the problem now. Come up with any answers. Yes, combinatorics is actually very exciting for me. So the statement of the problems are super simple, but coming up with a strategy to solve the problem is a different story, a whole different story. Okay, but here, of course, I have a lot of experience, but here I don't know how to guide you to find the result. Do you have any strategy? We can talk about that. What is your counting strategies here? Because you see, this problem seems a little bit a wild problem. Yes, there are many degrees of freedom you need to be considered and be worried about. No ideas. Okay, I can describe my strategy. I didn't hear you properly. Do you have a strategy?
I think I have one, but I can't find the exclamation mark in my calculator, so I can't find one.
Exclamation mark is not important. You can ask me and I can do it for you. But, okay, can you describe it at least?
No, because I'm very embarrassed over how.
Okay. So let me describe my strategy. And I think you don't learn combinatorics if you don't enjoy it and try to solve the problem from different angles. Okay, so one simple strategy is this. So let me write the numbers here for you. Let me change my colors to the proper colors.
Like I found the button. Is it 18,720?
No, it's much more than that. Yes. Okay.
Oh wait. Sorry. I think I have. I forgot.
Yes.
Is it 112,320?
112? No, events more than that.
Then
okay. So let us. Yes, please.
I have a question. Is this on A level or more than A level?
Yeah, it's more than A level.
Okay.
Yeah. So how many is you see the solution is super simple. I don't know how can I judge combinatorics, but from my experience, if I want to give you the answer to this problem, it is even less than half a line. So I don't know how to evaluate, how to assess the level of difficulty. But based on my experience, I know that these kind of problems are super simple sometimes to state, but very hard to solve. It's very hard when it comes to combinatorics. Judgment about the level is very hard. So this is, I told you that for this exam, I definitely exactly follow the book as I did for Math 4, if you remember. But this is another story. I told you that in Math 5, I will not bound myself to not talk about these things, but I'm assuming that the people who are taking this course, they are interested in mathematics. So I am also here to enjoy teaching mathematics for the people who are interested in listening mathematics. Okay, so but for the exam, if you are concerned about the exam, of course you should be. I will stick to the problems in the book, and every time I write on a school self which pages to read, which problems to do, if you do them, you are completely on the safe side. Okay, so my recommendation is that if you have taken Math 5, it means that you are interested in mathematics. Try to enjoy this 1 hour solving nice problems. So how many permutations of the numbers 1, 2 up to 9 are there such that no two of the numbers 1, 2, 3 are adjacent? Okay, let me solve it a very simple way. Of course, do you remember I talked about that we were able to solve the problem? I might be it's a very good idea to start the hard method first. So if you don't mind, let me duplicate this, and then let me first, I want to clean everything here so that we have enough space to solve the problems in different ways. Okay, do you remember, I think one idea, if I ask you the same question, it suddenly becomes, I don't know, a C-level question at the level of the book. If I just ask you, in how many permutations 1 and 2 are not adjacent, that's it. Then suddenly this problem becomes super simple. Instead of giving you 3 items not to be adjacent, I expect you should be able to answer my question immediately. So let me just open a box here. What happens if I only have one constraint? I don't want to have 1 and 2 next to each other. I don't care about 3 at all. Can you tell me what is the answer to this problem?
All permutations of the numbers minus the permutations where 1 and 2 are next to each other.
Yes, exactly. This I expect you to know, because we worked about this, some kind of this problem, this kind of problems is in the book, so you need to know about that. So the total number of permutation is how much? Is 9 factorial. Do you agree? And then the number of permutations in which 1 and 2 are close together, are adjacent, is easy, because let me write it. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Do you remember this package strategy? I put them in a package, then how many objects do I have? One package, 2, 3, 4, 5, 6, 7, 8 distinct objects, so it becomes 8 factorial, but I need to multiply by an extra 2 factorial because I have 2 options here, and this would be the answer. So I would write minus 2 factorial times 8 factorial, end of the story. Yes, this is a very simple problem, and we did it. I think most of you might think that this is also an option for this problem, and you are right. This is an option for this problem as well, but it becomes very complicated. But I think it's worth it, because if you go to technical university, you definitely have discrete mathematics, and then there you will see this is called inclusion exclusion principle. Okay, it's a big name for a very simple idea. Okay, let us try to use this. This method was the method of the complement rule. Let us use the same method to be able to solve this problem. But you need to have a very good understanding of what's going on. So what I do, I would draw a Venn diagram for myself. Okay, so I will draw a Venn diagram. For example, I would say that let us consider all permutations of all these numbers. I put them here. So for example, this point is one permutation, another point is another permutation. Okay? And then what I do, I will draw a circle here as a set. I will call it A. What is A? A is all permutations for which 1 and 2 are adjacent. There are some permutations in which 1 and 2 are adjacent. I collect all of them in this rectangle and put this in this bag, and I call it bag A. So what are they here for remembering what is happening? Let me write here 1 and 2 in one package. So this is A. So whatever you see here includes all those permutations in which 1 and 2 are close together. Sorry, adjacent. And now I want to do another bag in which 1 and 3 are adjacent. Let me ask your understanding. Do you think it is good to draw that one in this way, or should I have some intersection with this one? So can I say that, okay, let me repeat my question. I want to write B as the collection of all permutations containing, so in which 1 and 3 are adjacent. Do you think this is a good way of drawing, or I should have some intersection with that?
I mean, 3 can be 4, 1, so 3, 1, 2.
So answer my question. Intersecting or without intersection?
I think it should be more close.
Yeah, they should intersect. Yes, they should intersect. You are right, because there are some cases in which we have 1, 2, and 3. So this is one of those cases. So 1 and 2 are adjacent, 1 and 3 are adjacent. Okay, so it means that what I want to do, I draw this picture here, and I will call it B. Okay, so that's not, let me make it better. So here I have a little bit bigger. I don't know about the sizes. I am not saying that they should be into a scale, but forget about that. But this means that 1 and 3 are next to each other. Okay, and the same scenario, I will draw another circle or any kind of object. So for example, this one, and this I would call it C, in which 2 and 3 are adjacent. So if I ask you what is here, can you tell me what is here?
A, B, and C are next to each other?
1, 2, and 3, yes. Not A, B, and C.
I'm sorry.
Yeah, exactly. And then what I am interested in, can you tell me in this question which part of this rectangle I am interested in?
Everything around them.
Exactly, thank you. So that is exclusion inclusion principle. You will see I am interested in those things which are in none of these. Yes? Is that understandable for everyone? Good. Now, do you remember when I was teaching you set theory, I talked about the cardinality of this. So we learned about how to calculate the cardinality of the union of these sets. If you have forgotten, let me just write the formula here. It's the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of A intersection B minus the cardinality of A intersection C minus the cardinality of B intersection C, and then plus the cardinality of A intersection B intersection C. Yes, so this is what we learned. So if I calculate this, you see it is a very complicated object to calculate. So I have to calculate the number of elements inside everything here, which means the union, as you said, I need to consider outside of it. But it is easy. If I can calculate the number of elements here, which is a little bit complicated task because I have to calculate a lot of things. I have to include them, exclude them, include them. So this is why it's called inclusion and exclusion principle. Okay, I have to calculate a lot, 1, 2, 3, 4, 5, 6, 7 parts, then do them in this way. It will give me the number of elements in these sets, and then the total elements in this rectangle is 9 factorial. After that, I want to calculate this difference between this and that cardinality. Then I will definitely get my correct answer. Okay? Is that understandable for everyone?
Yes.
Okay, so but you see, it is possible to do, and sometimes it is inevitable. It's inevitable. This is why you spend some time in discrete mathematics in university to learn about exclusion and inclusion principle, because there are some problems that you can solve with them only in this way. I would recommend you to think in this way. This teaches you a lot, actually. Okay, but I just want you to tell you that if you want to use this naive idea, this is the correct way of doing it, and it is actually horrible. If I can find a simpler way, I definitely go for that, even though I recommend you to think about how to solve this problem in this way. It's extremely instructive if you are interested in combinatorics. But now, let me think a little bit better. It's a very simple way of solving this problem. I would say that, okay, let us forget momentarily about 1, 2, and 3 and concentrate about the rest of the numbers. What are the rest of the numbers? So then let me write all of them down once. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Momentarily, don't think about them. Only try to arrange these numbers. Okay. Assume that let me arrange them in one way. For example, I decide to put 5 here, and then I decide, let me just drop it to not confuse, and then I decide to put 8 here, and then I don't know, I decide to put 4 here, I decide to put 7 here, and then 9 here, and finally 6 here. This is one way of arranging the numbers from 4 up to 9, okay? This is one way. There is another way to do that. There is another way to do that. In how many ways I can do that? Can you tell me? I don't want to look here.
6 factorial.
Exactly. It's 6 factorial. Okay. It's 6 factorial ways that I can arrange these numbers. Okay, now can you see what happens? I intentionally put some... I wrote them a little bit far away from each other. Now, can you see what might be a good strategy to solve my problem now? Okay, so if it is not clear, let me give you a guide. Okay, so I am just intentionally do it slowly so that probably you can come up with your strategy. Nothing rings a bell?
We distribute 1, 2, and 3 into the boxes between the numbers.
Yes. Okay. And then you see that, should I consider this as an empty box here and there? So you see, first of all, agree, if I put 1, 2, and 3 in 3 of these boxes that you see, in any way that you like, you get to your goal. Yes, for example, I put 1 here, I decide to put 2 here, I decide to put 3 here. now look at the whole idea. Look, now do not look the empty boxes. Do not look the empty boxes. Okay, just look at the blue numbers and the filled boxes. Is what you get is one of the items that you want to get? Do you understand that? Is that understandable?
Yes.
Yes. So it is hopefully clear that I should also include this one, because if I do not put any empty space, it means that I am not allowed to start with 1. But in principle, yes, I am allowed to start with 1. So can you tell me now what is the number of ways that I can distribute 1, 2, and 3 in these boxes? This should be very quick. This is something. What is that?
7 ways.
So 1, 2, 3, 4, 5, 6, 7 places. These places are distinct. Why? Because I can say the box left to the 5. So this means this. Nobody get confused. I can say the box between 5 and 8. So this box is different from that box. This box is different from other boxes. So how many positions do I have? 1, 2, 3, 4, 5, 6, 7 distinct locations. How many objects I have? 3 distinct objects. I want to put 3 distinct objects in 7 empty locations.
With P7.
Yes, exactly. P7, thank you. P7 and 3. Okay, now I have 2 numbers. What should I do with these 2?
Multiply.
Multiply, exactly. So you see, this answer is half a line.
Is the final answer 907,200?
No, the answer that I get is 151,200. Okay, I can calculate this one for you. So you see, what do you consider this problem? Can you consider this problem a hard problem or not?
I meant the final answer, not that one.
This is the final answer. There is nothing to do anymore. If you understand what's going on, this is the finalized part. I don't know. If you don't understand, let me know. What is left then? There is nothing to be counted again, is it?
Baba,
Yes?
how did you come up with this strategy?
No, it is not easy. It is not easy. Of course, it is not. I mean, I have solved a lot of combinatorial problems because I love it, you know. But still, there are many problems even I don't understand. So I will come up with a problem. I don't know. Do you remember? I don't know how many of you even cared. Do you remember when I was talking about institutional? Do you remember? In the last session that I was in the school when we were talking about institutional, so I told you that my instinct tells me that there is a better way to do that. It was not easy for me at all to come up with another idea, but then I realized there is another idea. Actually, I consulted one of my books, who my friend wrote it in Iran, so I saw that there is a very nice strategy to come up with. Okay, but that is mathematics. This is the interesting part about the mathematics, actually. But I want you to I hope that you understand this. I don't know, do you consider this problem hard or not? Because if you just write this in the exam, I will give you the full mark.
No, like now that you solved it, it's very easy.
Yeah. Yeah, I understand, but I mean, this is up to you. If you are interested, you need to start working problems. All my life, I am sitting behind my desk solving problems. Okay, but still, there are many problems that I cannot solve or come up with an idea at all. Yes, that is the reason I am doing mathematics. I exactly like this part. In principle, when you like spicy food, Why do you like it? Because it burns your tongue, yes? That is exactly that sensation people like. Otherwise, why do you eat spicy food? So the reason that people do mathematics is because it is hard and it makes you suffer. And that is exactly comparable to why you eat spicy food. Okay. Any other questions? But now that you have this experience, what I'm saying is that if you are interested, you shouldn't be able to sleep this night unless you solve this problem using this method as well, and then it would be super exciting. It's not easy. There are many technical things that you need to take care. Then it would be very exciting at the end of the day if you get this answer. Then you appreciate this 1/2 a line solution even more. So that's my problem. So still I cannot sleep. I definitely do this after the lesson myself. Okay, so that's the problem. Now what I expect you is now you should be able in principle to solve the next problem coming. Okay? Any questions for this problem? Okay, so now let us go and make this is a little bit bigger, and I want to wait again. Of course, there are some differences with this problem and the other problem. I want to see how do you treat the problem without giving you a little bit of hint. Okay, so let me pause the video. Repetition actually plays a very important role here if you want to have the same strategy as I described you before. Of course, it has some effects, but is it crucially hard?
Not in this case, but it might be if the letters we don't want adjacent are repeated objects.
Yeah, exactly. That is why I took A away, so you realize that. Yes, but don't worry. We can solve harder problems later. But yeah, this is not very different, because can anyone except you, do you want to describe? Someone is there to describe what I want to do right now. First, what I do, I will start writing international in this way. International. Yes, no. Yes, I write this in this way. Now I see that I have 2 repetitions of I, 3 repetitions of, and etc. etc. Okay, but now after correction, R, E, and L shouldn't be adjacent at all. No 2 of them. Okay. So what I do, I would say that okay, I have the problem here, E, R, and L. Okay, but I have other objects, so let me arrange these objects. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 objects. I want to arrange them in a row. This is not a hard problem. It was a hard problem if you haven't studied permutations with repetition. Then it means that you need to solve that problem here, but you already know how to arrange them, yes? So for example, let me just give you a random arrangement of what is left. For example, I decide to put 1 I here, I decide to put 2 N's, I don't know, I have T here, I have O, A, O, now it's hard to keep track, I, so what is left then? Let me put another N and I here. So is that all? And let me keep the distance, N and I. Did I consider everything? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 is left. Which one is that? Can you see? Ah, there is an A again. So let me write A here. There is no space there. So this is one kind of permutations that I can consider for what is left over. Okay, and then you know this is not problematic for you if you have come up, if you have reviewed the lesson so far. How many ways I can arrange these letters? This is a standard problem in combinatorics. Okay, so what is the number of ways that I can arrange them? I have 10 objects. Some of them are repeated, But this is not a hard problem to come up with the answer. So the answer is 10 factorial. I have 10 objects, but some of them are repeated. A is repeated 2 times, so I have to divide by a 2 factorial. So let me start from here. 2 factorials because of I, 3 factorials because of n, 2 factorials because of t, and 2 factorials because of a. So everyone agrees with me. This is not a hard problem if I ask you arrange them. But then again, I think that you immediately realize that you can have that idea. Yes, you can have these boxes among them. Yes, and then how many boxes are there? You don't need to be very careful. Let us not waste time. So this is actually the places that I am allowed to choose for placing R, E, and L. Are these distinct positions? Don't get fooled by this that all of them are squares. Why they are distinct positions? Yes, they are distinct because you can address them. So you can say that, okay, this is the first position on the left, and then you see that this is the second position. Second position means between the next 2 letters coming, and then etc. and etc. But how many of them I need? I need only 3 of them. How many of them are there? If you count, it is 11. 1 more than the objects that you arrange first. So, and then you know the answer. The answer is P, 11, and 3. And then you multiply it. And I calculated with the calculator. I got this answer, and I think Alec also got that, so it couldn't be that coincidence. So yeah, you don't need, of course, to write that big number at all. I'm just writing it to confirm what we have done so far.
What?
Yes, please.
And why 11 and not 10? Because the last time you didn't consider.
No, if I did that, it is wrong for my side. Let me check. No, 1, 2, 3, 4, 5, 6, 7. No, that is 7.
And then,
okay, so did I make a mistake here? So this is 1, 2, 3. Yeah, yeah. So
yeah, I thought you missed one of them.
no. If it was the case, I was wrong. But you know that if you write 10, it means that you are not considering one of these as one of the possibilities. But yes, they can happen. If you drop this and don't consider this, it means that you are not considering the case in which the permutation starts with one of them. But why not? The permutation can indeed start with one of them. Any questions so far? Is that understandable? So this is one tool in your toolbox if you enjoy combinatorics. Otherwise, why you should care about the problem in the first place? Okay, now let us go to the next problem. I don't know. First of all, tell me, is there any question here? No? Okay, good. So let us go to the next problem. Again, you solve it and I solve it, and then give me your answers, or give me it in factorial form if it be exactly like mine. So let me stop the video. Okay, can you describe your strategy? But because this is exactly the same problem, a little bit different. Might be Carl is correct. I don't know. Let us check. Let us check. So here I want to write 12 permutations. It means that I need to have a string of 12 letters in which the order is important. If this is finished here, what would be the answer? If that is the question, it's an E-level question, by the way. How many 12 permutations of 26 English alphabet are there? The answer is simple. It is P of 26 and 12. Yes? This is the answer if there is no restrictions. But here, there are some limitations here. First of all, you are not completely free in your choices. You have to choose A, B, C, and D. Okay. Okay, so 4 of them should be A, B, C, and D. So if you write English alphabet, so let me write it A, B, C, D, and E, F up to Z. So the total number here is 26 English alphabets, yes? And now I want to have 12 permutations, so it means that I have to choose 12 letters, but I do not have freedom for 4 of them. 4 of them should be A, B, C, and D. Yes? Okay, so it's clear that I made a mistake. So it means that how many degrees of freedom I have for my choices? I have 8 degrees of freedom. Do you agree? So it means that I need to have 8. I have 8 degrees of freedom in my choices. So what I do, first of all, I left these things aside. Then I will have 22 left. And then from this 22, I want to choose 8 of them. Okay, this is my strategy. Let us see if it works or not. So I will say that I will have 22. Yes?
Can you see the sharp pivot answer? I'm not quite sure.
When I am recording, I cannot see. When I don't record, I can see. That's the problem.
Okay, is it?
So let me see, because if I click on it, then there would be a black thing in the... yes, I think you are right now. I can see it. Yes. Yeah, that's very good that you have written it in this way. So let us check. I think your answer is correct. Thank you. So what you are saying is that I have 22, but I want to choose 8 of them because I do not have any controls in these 4. I have to choose them. So I have only 8 choices out of 22 choices. So this is the number of arrangements that I have. Okay, so for example, you see 8 letters here. For example, you might decide to choose E, I don't know, F, T, G, T, L, K, 8 of them. 1, 2, 3, 4, 5, 6, and I don't know. For example, O and P. We don't know. This is one possibility of choosing, of selecting and arranging them. But again, I have to replace A, B, C, and D. This is a have to. I have to keep them. So I have to arrange them in these open spaces here. But how many open spaces you see? One more, yes? 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so Khulud, I don't understand the second part. So why did you write the second part like that? Why did you write 13? The 13 is not correct because do you understand? Because now 1, 2, 3, 4, 5, 6, 7, 8, but I have how many empty spaces? I have 8 empty spaces. Yes, the first part was completely correct. The second part is half correct, half wrong. So yes, so this becomes P. I have 9 and then I need 4 of them. So that is the correct answer. Everybody agrees? And then let me calculate this, see what is the answer. So might be Carl was also correct. So I think, let me check this one. Is it your answer, Carl? Is that your answer? So 22 shift this and 8 times 9 and shift this. Oops, I made a mistake. Shift P and 4. Let me see. 22 P8, 9 P4. And then the answer is 3.89888142 times 10 to power 13. Was it your answer, Alex? Because
Yes.
your order of magnitude was correct.
Yeah, it was.
I remember, yes. Okay, sorry for my mess because I myself made a mistake. So you realize what's going on. So you see, if you just write this answer, it's completely acceptable for me. Okay, any questions? Okay, let us see what is left for us. Okay, now we we have another type of problems, totally different problems, that doesn't rely on your counting skills, but it relies on your analytic skills, algebraic skills actually. Here, this is a different type of problem. We want to prove this identity. We want to show that this is equal to this plus r times this. This doesn't rely on counting at all. You just look at it as an identity. I usually, if I want to prove an identity, I will start from the more involved side and try to simplify it as much as possible so that I get to the other side. If it is not possible, I simplify the left-hand side and put it aside. I simplify the right-hand side and put it aside and try to show that these final expressions are the same. This is also possible, but let me try to start with the right-hand side, which is more involved. And before that, let me write the formula of P in front of your eyes. What was that? Pn and r is equal to what is here, factorial in the numerator, and the difference between these two numbers, factorial in the denominator. So this is the way that you need to interpret. So now the right hand side is equal to, for this one I just use the formula, so it becomes n factorial divided by n minus r factorial, and then plus, you see an r here, so let me just write it. Now what can I write for p of this expression? N is the same, but this time r minus 1 is playing the role of r. So you need to be careful from algebraic point of view. So I put n factorial in the numerator, but in the denominator I have the same n, but instead of r I have r minus 1, and you are enough experienced by now that you have to put it in a pair of brackets and factorial. Interrupt me if you don't understand something. Okay, before doing that, let me do some simplifications. For the first one, let us, for the time being, don't change anything. And then the other one, instead of writing r here, I can multiply it in the numerator, but be careful. You just have to write it in this way. You just juxtapose them. You cannot do anything with that. But here, this minus sign, I can write minus r plus 1. So this becomes n minus r plus 1 factorial. Okay, the next step, you see that on the right hand side you have one single expression, and one single expression is one fraction, but you have two fractions here. So the motivation is clear. I need to make them one fraction, so I have to have a common denominator. Yes, but this is easy, not hard, because let me write it. I copy and paste the first part. The numerator I cannot do anything, I just write it as a product. But in the denominator I write something, tell me if you agree with me. I write it as n minus r plus 1 times n minus r factorial. Is that understandable for everyone? Good. And now you see that the second denominator is actually the common denominator itself. So I can write this as the common denominator, n minus r plus 1 times n minus r factorial. And then I would ask myself, if I divide this in my head by this, then I will get this factor, so I have to multiply that factor in the numerator. Plus, this is exactly this, so I don't need to change anything at all. So if I divide this by that, it is 1 times. If I multiply it here, it is the same. Now, what I do, in the denominator, I collect it back again. This one multiplied by this one has another name, which was this one. So let me put it back because I don't need it anymore. In the numerator, what can I do? You can start multiplying. N factorial multiplied by n. I cannot write anything. I have to just write them. The next one, multiplying this by minus r is minus r times n factorial, and then finally plus n factorial. After it is done, there is one single term at the end, so I will write plus r times n factorial. But the nice thing is here, this one and that one are the same with positive signs, they are cancelled. And then what happens now? In the numerator, hopefully you see that this term is has n factorial, this term also has n factorial. I can factor n factorial out. So let me write it on the right hand side and open the pair of brackets here. If I pull this out and write it here, n is left. And then if I take this one out, 1 is left. In the denominator, I want to do a little bit of change. Do you agree with me if I write n plus 1 minus r and then factorial? Yes, they are exactly the same thing. This expression here is exactly this expression, so no problems. But can you say what can I write for the numerator? Yes?
Factorial.
What? N plus 1 factorial, you said. I didn't hear you. Yes, so if your answer is this, yes, that's correct. And then in the denominator, I will have n plus 1 minus r factorial. Do you have hard time to see that this is exactly p of n plus 1 and r? Why is that? If I ask you calculate p of n plus 1 and r from this formula, instead of n factorial, you would write n plus 1 factorial. And in the denominator, what you do, instead of n, you put n plus 1 and then minus r. And that is exactly this expression. So I am allowed to collect it back into this form, and that is exactly the left-hand side. Is that understandable?
Yes.
Okay. But the interesting and exciting thing is that be able to understand this formula without even calculating anything. Do you have any idea how? And this is the very, very strong tool in the hand of a person who studies combinatorics. There are some formulas that we cannot prove them analytically like this, but if we rely on our counting skills, then we can find this equality. So you need to count something in two different ways, but because you are counting the same thing in two different ways, the answers finally should match, and this will give rise to a combinatorial identity like that. And this is for me, it's very interesting and exciting to come up with a counting plan so that I can visualize this somehow.
Isn't the formula just saying that an increase in the number of places is equal to RP and R minus 1?
Okay, it might say something like this, but the point is that could you come up with the answer on the right hand side if you haven't seen that? Okay, how many? So here, let me move this a little bit lower. This is something I want you to learn, even though. Let me just move it here. If I need it, I will come up back to this. Another type of problems is this one. Okay, they don't ask you to prove something analytically. They give you an equation and there is some unknown. You are supposed to determine it. This is also simple analytically, yes. But let us see if we can come up with an idea why this is correct using counting skills. So let me consider n objects, n plus 1 objects, okay? So let me write it in this way. Let me write A, and let me choose B1, B2, up to Bn. In total, how many objects you see? you see n plus 1 objects, all of them are distinct. So if I ask you what is the meaning of p n plus 1 and r, what do you say? You would say this would be the number of r permutations of these objects. So it means that the total number of ways that I can choose r of them and then arrange them in a row, this will give me that number. Okay, but now I can I can, in my head, I can partition it into two types of permutations. Yes, some of them, when I choose this, some of them I choose A, and in some of them I do not choose A. Do you agree? Because when I want to write a permutation, an R permutation out of these objects, in some of them A appears in some position, and in some of them A does not appear. So I can, in my head, I can divide the total number. This picture is not into scale. I can divide it into two distinct parts, including A, not including A. Okay, now can you tell me which one is easier? Let me ask which one is easier first, then ask you that one. Okay, now this one is easier. Can you tell me if this number is n1 and this number is n2? Do you agree with me n1 plus n2? First of all, tell me this. Do you agree with me n1 plus n2 is equal to p n plus r, n plus 1 and r? Do you agree with me this one?
Yes.
Okay, so this is hopefully understandable for you. But can you tell me what is n1? How many items are in the first one? No, n1 is harder. Sorry, n2 is easier. Sorry. How many items are in n2?
P, N, R.
Exactly. Do you see the point? Let us read it again. I am interested in R permutations, but I am, for some reason, I don't like A. I want to have R choices, but I don't like to have A. So it means that I need to choose R objects from these N left objects. Do you agree with me or not? Everyone agrees? Okay, so this is, everyone agrees or no? Confirm that, yes or no?
Yes.
Okay, good. Say something. So now let us count the number of elements here. This would be a little bit harder. What is your strategy to count the number of elements here? I want to count all of them. That includes A. So you know that for R permutation, how many distinct positions I need? I need R distinct positions. R positions. But I am interested in counting those R permutations which include A. So what would be your strategy to solve this problem? Can you say something?
Since we want to include A,
yes,
means that one position must already be filled by A.
Exactly. How many options are available for A? R. And then after A is settled down, say for example A is here, I need to put the rest of it. But what is the rest of it?
For the rest we have R minus 1 positions to choose between. We have R minus 1. So
from how many objects?
N objects.
N objects. Is that the same thing here? Did you enjoy the problem? Yes. Now you see that it was not, and so this is a more advanced level of understanding equalities in combinatorics. I didn't do any algebraic work at all. I was considering what is the meaning of this number in combinatorics, and I was making a story for it. Okay? Of course, this needs experience. This is not easy at all. But for this problem, it was possible. And then I say that, okay, when I want to choose r from n plus 1, there are two cases. Either I choose this one or I don't choose them. It is clear that if I calculate this, the number of items here, the number of items here, and add them, this becomes the same number. On the one hand, I can immediately answer that, so this would be this number. On the other hand, based on this way of counting, this should be, the sum should be the number. So because I am counting the same thing in two different ways, definitely the answers should be the same. Is that understandable for everyone?
Yes. Mr. Babak, do you think that this formula was created using that very same story?
Might be. For this problem, I will definitely come to some identities that it is not possible. At least I haven't seen any analytic proofs for them. But using combinatorial arguments like this, it's called double counting strategies. I double count something in two different ways, the same thing in two different ways, then I come up with this idea that these two numbers have to be the same, and this gives rise to an identity. Here, I would say that this is a more interesting and more advanced way of looking at the problem, but this is also completely okay. So I wouldn't consider this problem an A-level problem. I don't know, even if A-level problem, if I consider these calculations hard, this can be an A-level problem. But if you can come up with some story like that, it means that the way that you have understood the problem in combinatorics is very advanced. Okay, so I would recommend you to take a screenshot from here and then try to solve this problem yourself. It is very easy. Here you are not supposed to prove any identities. You want to find n. This is solving an equation so that the left hand side becomes equal to the right hand side. And then we will start with solving this problem next time. Okay, so if you don't mind, let me stop this